Hello there, and welcome. Tonight I want to take you somewhere soft and starlit, where the long breath of Earth's orbit can be heard as a whisper in the dark. It's a question that sounds unlikely at first, perhaps even impossible when you first hear it. Why would our path around the Sun become more oval, more elliptical, year by patient year? But stay with me for a moment, because this isn't a story of alarm or cosmic catastrophe. No, this is something far more gentle, far more beautiful. This is a story about the quiet rhythms that rock our world through space, rhythms so slow that a human lifetime catches only the faintest note of their song. What if Earth's orbit was not a fixed circle, not a rigid track carved in the darkness, but something more like a sleeping rhythm, breathing in, breathing out, so slow we only feel it with centuries of listening? Perhaps the ellipse is a lullaby more than a line, a gentle sway more than a strict path, and perhaps, just perhaps, understanding this subtle dance might help us understand something profound about our place in the cosmos, about the way everything in space is connected by invisible threads of gravity and time. As we settle in together for this journey through the quiet mysteries of orbital mechanics, I'd love to know where you're listening from tonight. What corner of our gently spinning world holds you as you prepare for sleep? Is it late evening where you are, with stars just beginning to peek through the darkening sky? Or perhaps it's the deep middle of the night, when the world feels hushed and still, perfect for contemplating cosmic mysteries. Whatever time zone cradles you, whatever landscape surrounds you, know that you're part of this story we're about to explore together. And if you find comfort in these cosmic contemplations, if the gentle rhythm of these words helps ease you towards sleep while feeding your curiosity about the universe, consider giving this video a quiet like, perhaps subscribing to, join us for future journeys through space and time, and if you'd like, tap that notification bell softly, so we can meet again beneath these same stars, exploring new mysteries with the same gentle wonder. You see, the question of Earth's changing orbit isn't just an abstract scientific puzzle, though it certainly is that too. It's a question that connects us to the vast scales of cosmic time, to the patient movements of planets that have been dancing together for billions of years. When we talk about Earth's orbit becoming more elliptical, we're really talking about a conversation between worlds, a slow dialogue conducted in the language of gravity across the darkness of space. Jupiter whispers to us from hundreds of millions of miles away, its massive presence tugging ever so gently on our path. Saturn adds its voice to the chorus, and even our own moon, so close and familiar, plays its part in this celestial symphony. But let me ease your mind right from the beginning. When scientists say Earth's orbit is becoming more elliptical, they're not talking about some dramatic change that we need to worry about. The variations we're discussing tonight are so subtle, so gentle, that they unfold over tens of thousands of years. If you could somehow watch Earth's orbit from above, speeding up time so that centuries passed like seconds, you might see our path around the Sun breathing, becoming slightly more oval, then slightly more circular, then more oval again, in cycles that span longer than all of recorded human history. It's a change measured not in miles or even hundreds of miles, but in tiny percentages, in mathematical whispers that only our most sensitive instruments can detect. Think about it this way. If you drew Earth's orbit on a piece of paper, even at its most elliptical, you'd have trouble seeing that it wasn't a perfect circle with your naked eye. The eccentricity of Earth's orbit, which is the technical term for how oval-shaped it is, varies between nearly 0 and about 0.06. Right now, we're at about 0.07, which means our orbit is almost circular, just slightly stretched. And when I say Earth's orbit is getting more elliptical every year, we're talking about changes so small that they're measured in 0.010%. It's like watching a mountain grow, real, measurable, but so slow that generations of humans could live their entire lives without noticing any difference. Yet there's something profoundly moving about these tiny changes, isn't there? They remind us that nothing in the universe is truly fixed, that everything is in motion, everything is dancing with everything else. Our planet, this pale blue dot that Carl Sagan spoke of so eloquently, isn't just spinning through space on some predetermined track. It's responding to the gravitational songs of other worlds, adjusting its path in an endless cosmic ballet that's been going on since the solar system was young. Consider for a moment the sheer age of this dance. Our solar system formed about 4.6 billion years ago from a vast cloud of gas and dust that collapsed under its own gravity. As the Sun ignited in the centre of this swirling disk, the planets began to coalesce from the remaining material, each finding its own orbit, its own rhythm around our star. And from the very beginning, these orbits were not independent. They were and are interconnected, each planet's gravity reaching out across the void to influence the others in ways both obvious and subtle. Earth's orbit from those earliest days has never been perfectly circular. In fact, a perfectly circular orbit is essentially impossible in a solar system with multiple bodies. Every planet, every moon, every asteroid exerts some gravitational influence on every other object, creating what scientists call perturbations, tiny deviations from what would otherwise be simple, predictable paths. These perturbations add up over time, creating cycles within cycles, rhythms within rhythms, a cosmic fugue of incredible complexity and beauty. The story of how we came to understand these orbital variations is itself a journey worth taking tonight. For most of human history, we assumed the heavens were perfect and unchanging. The ancient Greeks imagined the planets moving in perfect circles, a belief that persisted for nearly 2,000 years. It wasn't until Johannes Kepler, working with the precise observations of Tycho Brahe in the early 1600s, discovered that planets actually move in ellipses, not circles, that we began to glimpse the true nature of orbital motion. But even Kepler, brilliant as he was, couldn't have imagined the subtle variations we're discussing tonight. He saw the ellipses as fixed, unchanging. It would take centuries more of observation, mathematical development, and eventually computer simulations to reveal that these ellipses themselves are alive, breathing, constantly adjusting in response to the gravitational symphony of the solar system. The mathematical framework for understanding these changes came from many minds over many years. Isaac Newton gave us the law of universal gravitation, showing how every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. Pierre-Simon Laplace developed the mathematics of perturbation theory, allowing astronomers to calculate how planets influence each other's orbits over time. And in the 20th century, Milutin Milankovitch connected these orbital variations to Earth's climate cycles, showing how tiny changes in our orbit could trigger ice ages and warm periods over geological time. Tonight, as you listen to these words and perhaps feel sleep beginning to gather at the edges of your consciousness, you're participating in this same tradition of wonder about our cosmic neighbourhood. The questions we're exploring together: why does Earth's orbit change? What causes these variations? What do they mean for us? Are questions that connect us to centuries of human curiosity about the night sky. And here's something beautiful to consider. The very atoms that make up your body, the carbon in your cells, the iron in your blood, the calcium in your bones, were all forged in the hearts of dying stars billions of years ago. You are, quite literally, made of cosmic material. The same forces that guide Earth's orbit through its slow variations also govern the behaviour of every atom in your body. You're not separate from this cosmic dance. You're part of it, made of it, participating in it with every breath you take. As we prepare to dive deeper into the specifics of Earth's orbital changes, let's take a moment to appreciate the profound peace of cosmic time. In our daily lives, we're often rushed, stressed, worried about deadlines and obligations. But when we zoom out to consider orbital mechanics, when we think in terms of thousands or millions of years, there's a different quality to time, isn't there? It becomes less urgent, more patient. The universe isn't in a hurry. These orbital changes we're discussing unfold with a patience that's almost incomprehensible to our human minds. Yet they unfold with absolute reliability, following the laws of physics with a precision that our best atomic clocks can barely match. This is one of the gifts of contemplating space and astronomical phenomena. It puts our human concerns into a different perspective. Not to diminish them, not to say they don't matter, but to cradle them in a larger context. Your worries, whatever they might be, exist within this vast, patient cosmos that has been cycling through its rhythms for billions of years and will continue long after we're gone. There's something deeply comforting in that thought, something that can help ease us towards sleep with a sense of peace and connection to something larger than ourselves. Now you might be wondering, and it's a perfectly reasonable question, why should we care about such tiny changes in Earth's orbit? If they're so small, so slow, do they really matter? The answer is both yes and no, and exploring that paradox will take us into some fascinating territory. On one level, these changes are so gradual that they have essentially no impact on our daily lives, or even on the lives of our great-great-grandchildren. The amount Earth's orbit becomes more elliptical in a single year is so minuscule that it would take sophisticated instruments and careful calculations to even detect it. But on another level, these tiny changes add up over geological time to create profound effects on our planet's climate. The ice ages that have periodically gripped our world, the warm interglacial periods like the one we're living in now, these are influenced by the slow breathing of Earth's orbit. The eccentricity variations we're discussing tonight are part of what scientists call Milankovitch cycles, named after the Serbian mathematician who first calculated their effects on climate in the early 20th century. These cycles work together in complex ways. There's eccentricity, which we're focusing on tonight, how elliptical or circular Earth's orbit becomes. There's obliquity, which is the tilt of Earth's axis, varying between about 22.1 and 24.5 degrees over a cycle of about 41,000 years. And there's precession, the slow wobble of Earth's axis that determines which hemisphere receives more direct sunlight during different parts of the orbit. Together, these cycles create a complex pattern of climate variation that has shaped the history of life on Earth. But let's not get ahead of ourselves. Tonight we're taking this journey slowly, patiently, the way the cosmos itself moves. We're not rushing toward conclusions or dramatic revelations. Instead, we're settling into the rhythm of cosmic time, allowing ourselves to float in the space between knowledge and mystery, between what we understand and what still fills us with wonder. Think about this. Right now, as you listen to these words, Earth is hurtling through space at about 67,000 miles per hour in its orbit around the Sun. That's about 30 kilometers per second if you prefer metric. We're all astronauts, really, riding this incredible spacecraft called Earth through the cosmos. And yet, because we're all moving together, because the motion is so smooth, we don't feel it at all. We can lie in our beds, perfectly still from our perspective, while actually racing through space at speeds that would seem impossible if we could somehow step outside and watch. This motion isn't random or chaotic, though it might seem that way if we could see all the influences at play. Every second, Earth is responding to the gravitational pull, not just of the Sun, but of every other object in the solar system. Jupiter, the giant of our planetary family, exerts the strongest influence after the Sun, despite being hundreds of millions of miles away. Its gravity reaches across that vast emptiness, though perhaps emptiness isn't the right word, since space is filled with gravitational fields, electromagnetic radiation, and the occasional particle of solar wind, and gives Earth the gentlest of tugs, slightly adjusting our path. Saturn adds its own influence, as does Venus, Mars, and even tiny Mercury. The Moon, our constant companion, pulls on us too, though its main effect is on Earth's rotation and tides rather than our orbit around the Sun. All of these influences combine, interfere, amplify, and cancel each other in patterns of stunning mathematical beauty. If you could somehow plot all these gravitational influences over time, you'd see something that looks almost like music made visible. Waves upon waves, frequencies combining and separating, creating beats and harmonics that play out over millennia. The detection and measurement of these orbital variations is a testament to human ingenuity and patience. We're talking about changes so small that for most of history, they were completely invisible to us. Ancient astronomers, brilliant as they were, working with nothing but their eyes and simple instruments, could track the planets and predict eclipses with remarkable accuracy. But the subtle breathing of Earth's orbit, that required technologies and mathematical techniques that wouldn't be developed until very recently in human history. Today, we measure Earth's position in space using a variety of incredibly sophisticated techniques. Radio telescopes track the positions of distant quasars, objects so far away that they serve as essentially fixed reference points against which we can measure our own motion. Laser ranging systems bounce beams of light off reflectors placed on the Moon by Apollo astronauts, measuring the Earth-Moon distance to within millimeters. Networks of GPS satellites, originally designed for navigation, provide precise timing signals that allow us to track tiny variations in Earth's rotation and orbit. And then there are the computer simulations, mathematical models of the solar system so detailed that they can predict planetary positions millions of years into the past or future. These simulations take into account not just the gravitational influences of all the major bodies in the solar system, but also effects from Einstein's general relativity, the slow loss of mass from the Sun as it converts hydrogen to helium and radiates energy into space, and even the tiny pressure of sunlight itself pushing on the planets. It's quite remarkable when you think about it. We've become precise enough in our measurements and calculations that we can detect changes in Earth's orbit that amount to a few kilometers difference in a journey of nearly 1 billion kilometers around the Sun each year. It's like being able to measure the thickness of a human hair from miles away, or detecting the growth of your fingernails in real time. But why does Earth's orbit change at all? Why isn't it fixed, constant, unchanging? The answer lies in the fundamental nature of gravity and motion in systems with multiple bodies. In physics, there's something called the two-body problem. If you have just two objects in space, like Earth and the Sun, with nothing else around, their orbital relationship is perfectly predictable and unchanging. The smaller object would orbit the larger in a perfect, unchanging ellipse forever, or at least until something from outside the system interfered. But add a third body, say Jupiter, and suddenly the mathematics becomes incredibly complex. This is called the three-body problem, and it's one of the most famous challenges in physics. There's no general solution that works for all possible configurations of three bodies. Instead, each specific case must be calculated numerically, step by step, and even tiny changes in initial conditions can lead to vastly different outcomes over time. This is what mathematicians call chaos, not randomness, but sensitive dependence on initial conditions. Our solar system doesn't have just three bodies, of course. It has 8 major planets, dozens of moons, thousands of asteroids, and countless smaller objects, all pulling on each other with gravity's invisible threads. The remarkable thing isn't that Earth's orbit changes, it's that these changes are as regular and predictable as they are. Despite the incredible complexity of the system, Earth's orbit remains stable over billions of years, varying only within relatively narrow limits. This stability isn't accidental. It's the result of what scientists call orbital resonances and dynamic feedback mechanisms that have developed over the age of the solar system. Orbits that were unstable have long since been cleared out. Objects in those orbits either collided with something else, were ejected from the solar system, or settled into more stable configurations. What we see today is the result of 4.6 billion years of cosmic natural selection, if you will, the survival of the most stable orbits. As you lie there tonight, perhaps feeling the gentle pull of sleep beginning to work its magic, consider that you're experiencing the same fundamental force that shapes Earth's orbit. The gravity that holds you to your bed, that gives weight to your blankets, that keeps your glass of water from floating away. This is the same gravity that reaches across hundreds of millions of miles to connect Earth with Jupiter, Saturn, and all the other wanderers in our solar system. You're not just observing this cosmic dance, you're part of it, held by the same invisible threads that weave the solar system together. The measurement of Earth's orbital eccentricity, that technical term for how elliptical our orbit is, has a fascinating history that spans centuries of human observation and innovation. Early astronomers could tell that something was varying, that the distance between Earth and the Sun changed throughout the year, but quantifying these changes precisely required generations of patient work. Today, we know that Earth's eccentricity varies between nearly 0, an almost perfect circle, and about 0.06, a slightly elongated ellipse, over cycles that last about 100,000 and 400,000 years. Right now, in our current epoch, Earth's orbital eccentricity is about 0.0117, which means we're in a relatively circular phase of the cycle. At our closest approach to the Sun, called perihelion, which occurs in early January, we're about 91.4 million miles from our star. At our farthest point, aphelion, in early July, we're about 94.5 million miles away. That's a difference of about 3.1 million miles, which might sound like a lot, but it's only about 3.3% of our average distance from the Sun. And here's something that might surprise you. This variation in distance has less effect on our seasons than you might think. Seasons are caused primarily by the tilt of Earth's axis, not by our distance from the Sun. In fact, Earth is actually closest to the Sun during winter in the Northern Hemisphere, and farthest during Northern Hemisphere summer. The Southern Hemisphere experiences the opposite, of course, being tilted toward the Sun when we're at perihelion, and away when we're at aphelion, which does make southern hemisphere seasons slightly more extreme than northern ones, but the effect is subtle. But over tens of thousands of years, as Earth's orbit becomes more and then less elliptical, these effects can compound with other orbital cycles to create significant climate changes. When eccentricity is high, the difference between perihelion and aphelion becomes more pronounced, which can amplify the effects of other orbital cycles. When eccentricity is low, as it is now, Earth's climate is somewhat more stable, less susceptible to the triggering of ice ages or sudden warming periods. The discovery of these connections between orbital variations and climate was one of the great scientific achievements of the 20th century, though the idea had been proposed much earlier. In the 1840s, French mathematician Joseph Adhémar suggested that ice ages might be caused by orbital variations. In the 1860s, Scottish scientist James Croll developed this idea further, calculating how orbital changes could affect the amount of sunlight reaching different parts of Earth. But it was Milutin Milankovitch, working in the early 1900s, without the benefit of computers or even electronic calculators, who painstakingly calculated the orbital variations going back hundreds of thousands of years, and showed how they correlated with geological evidence of past ice ages. His work was largely ignored for decades. It seemed too neat, too mathematical to explain something as complex as climate. But in the 1970s, analysis of deep-sea sediment cores revealed temperature variations that matched Milankovitch's predictions remarkably well, and his theory became widely accepted. This connection between Earth's orbital variations and climate is profound but subtle. We're not talking about dramatic, sudden changes that would threaten life on Earth. Instead, these are gentle nudges that, over thousands of years, can tip the balance between ice ages and warm periods. They work by changing the distribution of sunlight on Earth's surface, not the total amount of sunlight we receive, which stays nearly constant, but where and when that sunlight falls. For instance, when Earth's orbit is more elliptical and northern hemisphere summer occurs near aphelion, our farthest point from the Sun, northern summers become cooler. If this combines with other factors, like reduced axial tilt, which also makes summers cooler, it can lead to a situation where winter snow doesn't completely melt during summer. Year after year, snow accumulates, eventually compressing into ice, and an ice age begins. The process is slow, taking thousands of years, but it's inexorable once it starts. Conversely, when orbital conditions favour warmer northern summers, perhaps when Earth's orbit is more elliptical, and northern summer occurs near perihelion, combined with increased axial tilt, ice sheets begin to retreat. The ice melts faster than new snow accumulates, and the world warms. Again, this process takes millennia, not decades or centuries. It's important to understand that these natural orbital cycles have nothing to do with current climate change, which is happening far too quickly to be explained by orbital variations. The changes in Earth's orbit we're discussing tonight unfold over tens of thousands of years. While the warming we're experiencing now has occurred in just a century or two, that's a difference in timescale of a factor of 1,000 or more. Current climate change is driven by human activities, particularly the emission of greenhouse gases, not by orbital variations. But studying these orbital cycles does give us important context for understanding Earth's climate system. It shows us how sensitive our planet's climate can be to small changes in the distribution of solar energy. It reveals the complex feedbacks between ice, ocean, atmosphere, and land that can amplify small initial changes into major climate shifts. And it reminds us that Earth's climate has always been dynamic, always changing, though usually at a pace far slower than what we're witnessing today. As we continue our journey tonight through the mysteries of Earth's changing orbit, I want you to imagine yourself floating high above the solar system, looking down at the delicate dance of planets around our Sun. From this cosmic perspective, time moves differently. Years pass like seconds, centuries like minutes. You can see Earth tracing its path around the Sun, that path slowly breathing, becoming more oval, then more circular, in a rhythm as old as the solar system itself. Chapter 2. A Silk Thread. Around the Sun. The cosmic context. Consider the scale of what we're discussing, the vast reaches of time and space that frame this gentle story of orbital change. If the history of Earth were folded into a single day, starting at midnight with the planet's formation 4.6 billion years ago, then the first life wouldn't appear until about 4 a.m. Photosynthesis wouldn't develop until around 9 a.m. The first multicellular life wouldn't emerge until about 6 p.m. The dinosaurs would rule from about 10:40 p.m. until 11:40 p.m. And humans, we wouldn't appear until the last few seconds before midnight. Our entire recorded history, everything we think of as civilization, would flash by in the final fraction of a second. And yet, in that tiniest sliver of time, in just the last few moments of our metaphorical day, we've developed instruments sensitive enough to measure the slow breathing of Earth's orbit, to detect changes that unfold over periods longer than our entire existence as a species. Our modern instruments would blink on only in the final milliseconds of our compressed day, and yet they would still measure the soft drift of an orbit shaped by ages. Perhaps the ellipse is a silk thread, tensioned by time itself, and we've learned to feel its subtle vibrations. This is one of the most remarkable things about human consciousness, isn't it? We exist for just a cosmic moment, our individual lives lasting less than a century in a universe that measures time in billions of years, and yet we can comprehend these vast scales. We can calculate the positions of planets millions of years in the past or future. We can detect the echoes of the Big Bang in the cosmic microwave background radiation. We can measure the slow drift of continents and the gradual lengthening of Earth's day as tidal friction slowly transfers angular momentum from our planet to the Moon. Kepler's laws, Newton's gravity, Einstein's gentle corrections, these are simple ideas quietly profound that say our path is an ellipse that shifts, ever so slightly, under the murmurs of cosmic neighbours. Not a crisis, but a cadence, a rhythm as natural and inevitable as the beating of a heart or the breathing of lungs. Each of these great thinkers built upon the work of those who came before, adding new layers of understanding to our picture of orbital motion. Johannes Kepler, working in the early 1600s, discovered his 3 laws of planetary motion through years of painstaking calculation, trying to make sense of the precise observations of Mars made by Tycho Brahe. His first law states that planets orbit in ellipses with the Sun at one focus. His second law tells us that a line connecting a planet to the Sun sweeps out equal areas in equal times, meaning planets move faster when they're closer to the Sun and slower when they're farther away. His third law relates a planet's orbital period to its average distance from the Sun in a precise mathematical relationship. These laws were revolutionary because they broke with 2,000 years of belief in circular orbits. The ancient Greeks had believed that the heavens were perfect, and that the circle, being the most perfect shape, must govern celestial motion. Even Copernicus, who correctly placed the Sun at the centre of the solar system, retained circular orbits in his model. Kepler's ellipses were a radical departure, and it took courage to propose them in the face of such long-standing tradition. But Kepler could only describe planetary motion. He couldn't explain why planets moved in ellipses. That explanation had to wait for Isaac Newton, who showed that Kepler's laws were natural consequences of universal gravitation. Newton's great insight was that the same force that causes an apple to fall from a tree also keeps the Moon in orbit around Earth, and Earth in orbit around the Sun. Gravity is universal, affecting everything with mass, reaching across the vast emptiness of space with a strength that decreases with the square of distance but never truly reaches zero. Newton's law of universal gravitation was elegant in its simplicity. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. From this simple law, all of Kepler's complex observations could be derived mathematically. The elliptical orbits, the varying speeds, the relationship between period and distance, all of it flowed naturally from Newton's equations. But even Newton's beautiful theory wasn't quite complete. In the early 20th century, Albert Einstein showed that gravity isn't really a force in the traditional sense, but rather a curvature of space-time caused by mass and energy. Massive objects like the Sun create valleys in the fabric of space-time, and planets orbit by following the straightest possible path through this curved geometry. It's a mind-bending concept, but it makes predictions that differ slightly from Newton's, and these tiny differences have been measured and confirmed. For our purposes tonight, discussing Earth's slowly changing orbit, Einstein's corrections are tiny, almost negligible. They add a small additional precession to planetary orbits, a slow rotation of the ellipse itself, but this effect is minuscule compared to the gravitational perturbations from other planets. Still, it's part of the complete picture, another thread in the complex tapestry of orbital dynamics. In the quiet depths of space, planets sway to resonances like slow chords held for millennia. These resonances are special relationships between orbital periods where planets repeatedly align in similar configurations. For example, Jupiter and Saturn come into conjunction, appearing close together in Earth's sky about every 20 years. This regular alignment means their gravitational influences on other planets, including Earth, create repeating patterns that can build up over time. These orbital resonances are found throughout the solar system. Neptune and Pluto are locked in a 3.2 resonance, meaning Neptune completes 3 orbits for every 2 of Pluto's, which keeps them from ever colliding despite their crossing orbital paths. Jupiter's moons, Io, Europa and Ganymede, are in a 4-2-1 resonance, completing 4, 2 and 1 orbit respectively in the same time period. These resonances aren't coincidences, they're stable configurations that have developed over billions of years through gravitational interactions. The Sun is the steady lantern at the centre of it all, containing 99.6% of the solar system's total mass. Its immense gravity dominates the motion of everything else, from massive Jupiter down to the tiniest asteroid. We trace our loop around this stellar anchor, a little nearer here at perihelion, a little farther there at aphelion, our path constantly adjusted by the gentle pulls of our planetary neighbours, but always bound to our star. And we, so small and yet included, notice we are part of this patient geometry, never insignificant, always connected. Every atom in our bodies feels the sun's gravity, responds to it, is held by it. We are not observers standing outside the system. We are participants, made of the same matter, governed by the same forces, dancing to the same cosmic rhythms. The discovery that Earth's orbit changes over time came slowly, built from centuries of increasingly precise observations. Ancient astronomers could track the positions of planets with remarkable accuracy, predicting eclipses and conjunctions years in advance. But they were limited by the precision of their instruments and the span of their observations. Detecting changes that unfold over millennia requires either observations spanning millennia or instruments precise enough to detect tiny annual changes. By the 18th and 19th centuries, astronomers had both better instruments and centuries of accumulated observations to work with. They began to notice discrepancies between predicted and observed planetary positions that couldn't be explained by the simple two-body interactions between planets and the Sun. These discrepancies led to the development of perturbation theory, mathematical methods for calculating how multiple gravitational influences combine to affect orbital motion. One of the great triumphs of perturbation theory was the discovery of Neptune in 1846. Astronomers had noticed that Uranus wasn't quite where it should be, according to predictions that accounted for the gravitational influences of all known planets. French mathematician Urbain Le Verrier and English mathematician John Couch Adams independently calculated that these discrepancies could be explained by the gravitational pull of an undiscovered planet. When astronomers pointed their telescopes to the predicted location, there was Neptune, exactly where mathematics said it should be. This same mathematical framework that revealed Neptune also showed that planetary orbits undergo slow, cyclic changes. The eccentricity of Earth's orbit, how elliptical it is, varies over periods of about 100,000 and 400,000 years. The tilt of Earth's axis varies over about 41,000 years. The direction Earth's axis points processes like a spinning top over about 26,000 years. These cycles, now known as Milankovitch cycles, combine in complex ways to affect the amount and distribution of solar energy reaching Earth's surface. The calculation of these orbital variations requires extraordinary mathematical sophistication. We're not just calculating the current positions and velocities of all the planets. We're projecting their mutual interactions forward and backward in time over millions of years. Each planet affects every other planet, and these effects, while individually tiny, accumulate over time in complex patterns. Modern computers have revolutionized our ability to calculate these orbital variations. What once took mathematicians years of hand calculation can now be done in seconds. We can simulate the entire solar system in exquisite detail, tracking the position of every major body over millions of years. These simulations have revealed subtle patterns and resonances that would have been impossible to discover through observation alone. For instance, we now know that there's a particularly stable resonance in Earth's orbital eccentricity with a period of about 405,000 years. This cycle is so regular that geologists use it as a kind of astronomical clock, dating ancient rock layers by identifying this rhythm in sediment deposits. Rocks from hundreds of millions of years ago show the same 405,000-year beat that we calculate from orbital mechanics, a beautiful confirmation that our understanding of planetary dynamics is correct. But perhaps the most profound aspect of these orbital variations is how they connect the cosmic to the terrestrial. Changes in Earth's orbit affect the amount and distribution of sunlight reaching our planet's surface, which in turn affects climate, weather patterns, ocean currents, and ultimately the conditions for life itself. The advance and retreat of ice ages, the rise and fall of sea levels, the shifting of climate zones, all of these are influenced by the slow breathing of Earth's orbit. This doesn't mean orbital variations control everything about Earth's climate. Our planet's climate system is incredibly complex, with many factors beyond orbital mechanics playing important roles. Volcanic eruptions can cool the planet by injecting aerosols into the stratosphere. Changes in ocean circulation can redistribute heat around the globe. The concentration of greenhouse gases in the atmosphere affects how much heat Earth retains. Life itself, through processes like photosynthesis and respiration, affects atmospheric composition and climate. But orbital variations provide the background rhythm, the slow beat against which these other factors play out. They're like the bass line in a complex piece of music, not always the most noticeable element, but fundamental to the overall structure. And just as a bass line can sometimes step forward to become the dominant theme, orbital variations can sometimes trigger major climate transitions when conditions are right. The study of past climate changes preserved in geological records has revealed fascinating connections between orbital cycles and Earth history. Ice cores from Antarctica and Greenland contain tiny bubbles of ancient atmosphere, allowing scientists to measure past concentrations of greenhouse gases and relate them to temperature and orbital variations. Ocean sediments preserve the shells of microscopic organisms whose chemistry reflects the temperature and ice volume of ancient seas. Cave formations like stalactites and stalagmites record changes in precipitation and temperature in their growth patterns. All of these records tell a consistent story. Earth's climate dances to orbital rhythms. Not in a simple mechanical way. The relationship is complex, with feedbacks and thresholds and tipping points, but the connection is undeniable. When we look at temperature records going back hundreds of thousands of years, we see the signature of orbital variations written clearly in the data. One of the most striking features of these climate records is how abrupt some of the changes can be. While orbital variations themselves change slowly and smoothly, climate can sometimes shift rapidly from one state to another. It's as if Earth's climate system has multiple stable states, like a ball that can rest in different valleys. And orbital variations can sometimes provide just enough of a push to send the climate rolling, from one valley to another. These abrupt changes remind us that Earth's climate system is not linear. Small changes in orbital parameters can sometimes trigger large changes in climate through positive feedback mechanisms. For instance, when orbital conditions favour cooling, ice sheets begin to grow. Ice reflects more sunlight than land or water, so as ice sheets expand, Earth absorbs less solar energy and cools further, allowing ice sheets to grow even more. This ice albedo feedback can amplify a small initial cooling into a full-fledged ice age. Similarly, when orbital conditions favour warming, melting ice exposes darker land and ocean underneath, which absorb more sunlight and accelerate the warming. Warming oceans release dissolved carbon dioxide into the atmosphere, enhancing the greenhouse effect and causing more warming. Melting permafrost releases methane and carbon dioxide that have been locked away for thousands of years, adding to the warming. These positive feedbacks can turn a gentle orbital nudge into a major climate transition. But there are also negative feedbacks that provide stability, preventing runaway cooling or warming. As ice sheets grow, they depress the land beneath them, eventually lowering their surfaces to warmer altitudes where melting increases. As the planet warms, increased evaporation leads to more clouds, which reflect sunlight and provide cooling. The Earth system is full of these competing feedbacks, creating a complex dance between stability and change. Understanding these feedbacks and their interaction with orbital variations has practical importance for predicting future climate. While current climate change is driven primarily by human activities, not orbital variations, the same feedback mechanisms that amplify orbital signals also amplify human-caused warming. By studying how Earth's climate responded to orbital forcing in the past, we can better understand how it might respond to human forcing in the future. The precision with which we can now calculate past and future orbital variations is truly remarkable. We can predict Earth's orbital parameters millions of years into the future with high confidence, and we can calculate them millions of years into the past with good accuracy, though uncertainty grows the further back we go due to the chaotic nature of the solar system. This ability to peer deep into Earth's orbital past and future is like having a time machine for planetary motion. These calculations reveal that we're currently in a relatively stable period of Earth's orbital evolution. Our orbit's eccentricity is low and changing slowly. The other orbital parameters are also in configurations that favour climate stability. In fact, without human influence, Earth would likely be slowly cooling toward the next ice age over the coming millennia, though this natural cooling is completely overwhelmed by current human-caused warming. Chapter 3. The ellipse that breathes. Earth's eccentricity through deep time. It's a question that seems too neat, perhaps too simple when first considered. More elliptical every year. But the truth is a tender tapestry far more complex and beautiful than any simple trend could capture. Earth's orbital eccentricity ebbs and flows over tens of thousands of years, like a shoreline breathing with ancient tides, advancing and retreating in patterns that span longer than all of human civilization. And yet, on human timescales, even near zero drift is a story worth telling, a whisper of change that connects us to the vast cycles of cosmic time. Scientists have found repeating rhythms in Earth's orbital eccentricity, the Milankovitch cycles we've touched upon, where eccentricity waxes and wanes in overlapping periods of roughly 100,000 and 400,000 years, braided with the precession of Earth's axis and changes in axial tilt. These aren't simple sine waves, neat and predictable, but complex patterns that emerge from the gravitational conversations between worlds. Data reveals a particularly prominent 405,000-year metronome, steady as a heartbeat in stone, so reliable that geologists use it to date rock layers hundreds of millions of years old. Consider the possibility that each year's change in Earth's orbital eccentricity is like a single grain of sand in a vast hourglass, almost imperceptible on its own, but meaningful when held against deep time. If you could watch Earth's orbit for a single year, even with the most sensitive instruments, you might barely detect any change at all. The eccentricity might shift by a few parts per billion, a change so small it's like watching a mountain grow by the width of an atom. But give it time, 10,000 years, 100,000, a million, and these atomic changes accumulate into something significant, something that can reshape the face of our planet. What if, just maybe, this slow breath is part of why our world feels seasons, climates, and eras, each a stanza in a poem we're still learning to read? The ice ages that have punctuated Earth's history, the warm periods that allowed civilizations to flourish, the gradual shifts in rainfall patterns that turned forests to grasslands and back again, all of these are influenced by the patient breathing of Earth's orbit, combined with other factors in a dance of extraordinary complexity. To truly appreciate the scale and subtlety of these changes, we need to journey deep into Earth's past, to see how orbital eccentricity has varied over geological time. The story written in rocks and ice and ocean sediments stretches back hundreds of millions of years, though it becomes harder to read the further back we go, like ancient text fading on weathered stone. In the most recent geological period, the Quaternary, which began about 2.6 million years ago, Earth has experienced a series of ice ages separated by warmer interglacial periods. We're currently living in an interglacial called the Holocene, which began about 11,700 years ago when the last ice age ended. During the ice ages, massive ice sheets covered much of North America and Europe, reaching as far south as New York City and London. Sea levels were hundreds of feet lower than today because so much water was locked up in ice. The landscape would have been unrecognizable to us, with different coastlines, different rivers, different ecosystems. These ice ages follow a complex rhythm that correlates strongly with orbital variations, particularly eccentricity. When Earth's orbit is more elliptical, the difference in solar radiation between perihelion and aphelion becomes more pronounced. This doesn't change the total amount of sunlight Earth receives over a year, but it does change how that sunlight is distributed between seasons and hemispheres. When this combines with other orbital factors, like where in the orbit the seasons occur due to axial precession and how tilted Earth's axis is, it can create conditions that either favour or discourage the growth of ice sheets. The relationship isn't simple or deterministic. Earth's orbit doesn't directly cause ice ages. Rather, orbital variations create conditions that make ice ages more or less likely. It's like setting the stage for a play. The orbital configurations provide the setting, but whether an ice age actually occurs depends on the actors: greenhouse gas concentrations, ocean currents, volcanic activity, and myriad other factors. Sometimes the stage is set for an ice age, but it doesn't happen because other factors aren't aligned. Sometimes a relatively small orbital trigger can cause a major climate shift because the Earth system is poised at a tipping point. The discovery of this connection between orbital variations and ice ages is one of the great detective stories of science. In the 1970s, a team of scientists analysed ocean sediment cores that contained the shells of tiny marine organisms called foraminifera. The chemical composition of these shells, particularly the ratio of oxygen isotopes, provides a record of past ocean temperatures and ice volume. When they analysed the patterns in this data, they found clear cycles matching the periods predicted by Milankovitch theory. About 23,000 years for precession, 41,000 years for axial tilt, and 100,000 years for eccentricity. But there was a puzzle. The 100,000-year eccentricity cycle showed up most strongly in the data from the last million years, even though the actual variation in solar radiation caused by eccentricity changes is quite small compared to the other cycles. Why should the weakest orbital forcing produce the strongest climate signal? This is known as the 100,000-year problem, and it's still not completely solved, though scientists have proposed various mechanisms involving feedback processes and threshold effects that could amplify the eccentricity signal. One possibility is that eccentricity acts as a modulator of the precession cycle. Precession determines where in Earth's orbit the seasons occur, but this only matters if the orbit is eccentric. When Earth's orbit is nearly circular, it doesn't much matter where in the orbit summer or winter occurs because the distance from the Sun is almost constant. But when the orbit is more elliptical, precession becomes important, determining whether a hemisphere's summer occurs when Earth is close to or far from the Sun. So eccentricity, while not directly causing large changes in solar radiation, controls how effective precession is at driving climate change. The 405,000-year eccentricity cycle, which is more stable and predictable than the shorter cycles, leaves particularly clear signatures in the geological record. This cycle is driven primarily by the gravitational influence of Jupiter and Venus, the two most massive planets in the inner solar system from Earth's perspective. Because Jupiter's orbit and Venus's orbit are relatively stable, their combined effect on Earth's orbit creates this remarkably regular beat that has persisted for hundreds of millions of years. Geologists have found evidence of this 405,000-year cycle in rock formations dating back to the time of the dinosaurs and beyond. In the Newark Basin of New Jersey, for example, layers of sedimentary rock laid down over 30 million years during the late Triassic and early Jurassic periods show clear evidence of orbital cycles, including the 405,000-year eccentricity beat. These rocks formed in ancient lakes that expanded and contracted with climate changes driven by orbital variations, leaving a record in the alternating layers of different sediment types. Even more ancient rocks show similar patterns. In Western Australia, banded iron formations that are over 2.5 billion years old show cyclical patterns that may reflect orbital variations from Earth's deep past. Though Earth's rotation was faster then and the Moon was closer, affecting the specific periods of orbital cycles, the fundamental processes were the same. Gravity shaped orbits then as it does now, creating rhythms that influenced climate and sedimentation. This deep time perspective reveals something profound. Earth's orbit has been breathing for as long as Earth has existed. The specific patterns have changed as the solar system evolved, as the Moon migrated outward, as Earth's rotation slowed, but the fundamental phenomenon of orbital variation has been constant. It's a thread connecting us to Earth's earliest days, a continuity across billions of years of change. The measurement and calculation of these orbital variations requires extraordinary precision. Modern techniques can detect changes in Earth's orbital parameters that amount to fractions of a percent over decades. Space-based telescopes measure the positions of stars with such accuracy that we can detect the tiny wobble in Earth's motion caused by the Moon's orbit. Laser ranging to the Moon, Mars, and artificial satellites provides distance measurements accurate to centimeters over hundreds of thousands of kilometers. These measurements feed into sophisticated computer models that integrate the equations of motion for all the major bodies in the solar system. The calculations must account not just for Newtonian gravity, but also for effects from general relativity. The fact that the Sun is slowly losing mass as it converts hydrogen to helium, tidal interactions between planets and their moons, and even the pressure of sunlight on planetary surfaces. Each of these effects is tiny, but over millions of years they add up to measurable changes in orbital parameters. The most advanced of these models can reliably calculate Earth's orbital variations going back about 50 million years and forward about 20 million years. Beyond these limits, the chaotic nature of the solar system makes precise predictions impossible. Small uncertainties in current positions and velocities grow exponentially over time, eventually overwhelming our ability to make specific predictions. It's not that the solar system becomes random, it still follows the laws of physics precisely, but that tiny differences in initial conditions lead to completely different outcomes over very long timescales. This chaos doesn't mean Earth's orbit will suddenly become wildly elliptical, or that Earth will be flung out of the solar system. The chaos is bounded, orbital parameters vary within limited ranges, and the overall stability of the solar system is maintained. It's more like weather than like an explosion. We can't predict exactly what Earth's eccentricity will be 100 million years from now, just as we can't predict the weather a year from now, but we can be confident it will fall within certain bounds. The study of orbital variations in other planetary systems has given us new perspective on our own. Astronomers have now discovered thousands of planets orbiting other stars, and many of these systems look nothing like ours. Some have giant planets in highly elliptical orbits that would destabilize any Earth-like planets in the system. Others have planets in complex resonant chains, their orbits locked together in precise mathematical relationships. Still others have planets so close to their stars that they complete orbits in just a few days. This diversity makes us appreciate the relative stability and regularity of our own solar system. Earth's orbital variations, while significant enough to influence climate over geological time, are gentle compared to what's possible. We don't experience the wild swings between freezing and roasting that a planet in a highly eccentric orbit would face. Our orbital changes unfold slowly enough that life can adapt, that evolution can keep pace with environmental change. The question of how orbital variations might change in the future is fascinating to contemplate. Over the next few million years, we expect Earth's eccentricity to continue its current cycles, becoming more and then less elliptical, with the familiar periods of 100,000 and 400,000 years. The 405,000-year cycle, being particularly stable, should continue its steady beat far into the future. But over longer timescales, things become less certain. The Moon is slowly moving away from Earth due to tidal friction, which will eventually affect the stability of Earth's axial tilt. In about 1 billion years, the Moon will be far enough away that it can no longer stabilize Earth's obliquity, potentially allowing our axial tilt to vary chaotically. This could lead to extreme climate variations that would make current ice age cycles look gentle by comparison. The Sun itself is slowly growing brighter as it ages, increasing by about 10% every billion years. This gradual brightening will eventually overwhelm any cooling effects from orbital variations. In about 1 billion years, Earth may become too hot for liquid water regardless of orbital configuration. But that's a story for another night, a mystery for future beings to contemplate if they exist. For now, for the next few million years at least, Earth's orbit will continue its patient breathing, its slow drift between more and less elliptical configurations. Each year adds its grain of sand to the hourglass, each century its whisper to the conversation. We humans, brief visitors that we are, have learned to hear these whispers, to read the story written in stone and ice, to understand our place in the grand cycles of cosmic time. The practical implications of understanding orbital variations extend beyond satisfying scientific curiosity. By understanding how Earth's climate responded to orbital forcing in the past, we can better predict how it might respond to other forcings in the future. The same feedback mechanisms that amplify orbital signals, ice albedo feedback, carbon cycle feedbacks, water vapor feedback, also amplify human-caused climate change. The past is a laboratory where we can study these feedbacks in action, learning lessons that apply to our current situation. Paleoclimatologists, scientists who study past climates, use orbital variations as a kind of clock for dating ancient climate events. If they can identify orbital cycles in a sequence of sediments or ice layers, they can determine the time span represented by those layers. This technique, called orbital tuning or astronomical dating, has revolutionized our ability to create detailed chronologies of Earth history going back millions of years. The study of orbital variations also helps us understand the conditions necessary for habitability on planets orbiting other stars. A planet needs to maintain liquid water on its surface for billions of years for life as we know it to evolve. This requires not just being at the right distance from its star, but also having a stable enough orbit that climate doesn't vary too extremely. The orbital dynamics that keep Earth habitable might be rarer than we once thought, making our world even more precious. As you drift towards sleep tonight, perhaps you can feel yourself part of this vast, slow rhythm. Your body, made of atoms forged in ancient stars, rests on a planet that itself rests in an orbit that breathes with the patience of geological time. Every breath you take, every heartbeat, happens within this larger breathing, this cosmic rhythm that connects you to everything else in the solar system. The eccentricity of Earth's orbit right now, at this moment, is about 0.0167. It's decreasing very slightly, becoming more circular, though the change is so slow you could watch for your entire lifetime and barely notice a difference. We're about halfway between the minimum eccentricity of near zero and the maximum of about 0.06 that Earth's orbit reaches during its cycles. It's a quiet time, orbitally speaking, a gentle phase in the long breathing of our planet's path around the Sun. In about 27,000 years, Earth's orbit will reach a minimum eccentricity, becoming nearly circular. Then it will begin to grow more elliptical again, reaching another maximum in about 100,000 years. These future changes will unfold with the same patience that has characterized Earth's orbital evolution for billions of years, unhurried, inevitable, following the laws of physics with mathematical precision. But numbers and timescales can only tell part of the story. There's poetry in these orbital variations, a kind of cosmic music that plays out over millennia. Each planet contributes its voice to the symphony, from Mercury's quick soprano to Neptune's bass profundo. Earth's orbit responds to all these voices, adjusting its shape in a complex harmony that never exactly repeats, but always follows the same underlying rules. Now imagine Jupiter and Saturn as distant cellists, drawing long, low notes across the cosmos that coax our orbit's shape to sway ever so gently. These giant planets, so far away that their light takes dozens of minutes to reach us, extend their gravitational influence across the vast emptiness of space, touching Earth with forces so subtle that it took humanity thousands of years to even realize they existed. Scientists have observed their gravitational nudges stacking into quiet secular trends, like ripples overlapping on a still lake at dawn, each wave barely perceptible on its own, but combining to create patterns of profound beauty and consequence. Jupiter, the king of planets, contains more mass than all the other planets combined. At 318 times Earth's mass, it's a giant among giants, a world so large that over 300 Earths could fit inside it. And yet, despite its enormous size, Jupiter orbits the Sun at an average distance of about 484 million miles, more than 5 times farther from the Sun than Earth. At that distance, you might think Jupiter's gravitational influence on Earth would be negligible, lost in the vastness of space. But gravity, patient and persistent, reaches across any distance, growing weaker with the square of distance but never truly reaching zero. The gravitational force between Earth and Jupiter is indeed tiny compared to the Sun's grip on our planet. The Sun's gravity on Earth is about 28,000 times stronger than Jupiter's. But here's the beautiful subtlety of celestial mechanics. We don't feel the direct pull of Jupiter so much as we feel the difference between Jupiter's pull on Earth and its pull on the Sun. This differential force, called a tidal force, is what actually perturbs Earth's orbit, causing it to deviate ever so slightly from the perfect ellipse it would follow if the Sun and Earth were alone in the universe. Saturn, the ringed beauty of our solar system, adds its own voice to this gravitational chorus. At 95 times Earth's mass, Saturn is smaller than Jupiter, but still massive enough to make its presence felt across the solar system. Orbiting at an average distance of about 890 million miles from the Sun, Saturn is nearly twice as far from us as Jupiter, which means its direct gravitational influence on Earth is even smaller. But Saturn and Jupiter don't work in isolation. They work together, and sometimes their combined effects are greater than the sum of their parts. Data suggests that resonances, subtle alignments of timing, guide the 405,000-year cycle, a cosmic pendulum confirmed in sediments and in careful models by researchers like Jacques Lascar and colleagues at the Paris Observatory. Lascar's work, spanning decades of increasingly sophisticated calculations, has revealed the intricate web of gravitational relationships that shape Earth's orbital evolution. His models show how Jupiter and Venus, despite being at very different distances from Earth, work together to create the remarkably stable 405,000-year eccentricity cycle that geologists find written in rocks hundreds of millions of years old. The concept of resonance in orbital mechanics is both simple and profound. When two orbiting bodies have periods that form a simple ratio, like 2:1 or 3:2, they repeatedly encounter each other in similar configurations. These repeated encounters can amplify small gravitational effects, like pushing a child on a swing at just the right moment to make them go higher. In the case of Earth's orbital eccentricity, the relevant resonances are more subtle, involving not just orbital periods, but also the rates at which orbital orientations change due to gravitational perturbations. Jupiter and Saturn themselves are in a near resonance known as the Great Inequality, where 5 orbits of Jupiter, 59.3 years, nearly equal 2 orbits of Saturn, 58.9 years. This near resonance causes their combined gravitational effect on the inner solar system to pulse with a period of about 900 years. While this particular cycle doesn't directly drive Earth's eccentricity variations, it's part of the complex gravitational symphony that shapes all planetary orbits over time. Missions such as Juno and Cassini have refined our understanding of these giant planets, improving measurements of their masses, internal structures, and gravitational fields. Juno, currently orbiting Jupiter, has revealed that the giant planet's interior is more complex than previously thought, with a dilute core that extends partway toward the surface rather than a compact core at the center. This affects Jupiter's gravitational field in subtle ways that must be accounted for in precise orbital calculations. Cassini spent 13 years orbiting Saturn from 2004 to 2017, providing unprecedented detail about the ringed planet and its moons. Among its many discoveries, Cassini made precise measurements of Saturn's gravitational field, revealing tiny variations that tell us about the planet's internal structure and rotation rate. These measurements feed into the models that calculate how Saturn's gravity affects other planets over millions of years. The spacecraft's final orbits, diving between Saturn and its rings before plunging into the planet's atmosphere, provided gravitational measurements of extraordinary precision. Perhaps the giants do not command but suggest, and Earth listens, leaning a little more oval, then a little less, across the soft centuries. This is a beautiful way to think about gravitational perturbations, not as forces imposed upon Earth, but as gentle suggestions that Earth incorporates into its dance around the Sun. The changes are so gradual, so patient, that if you could somehow stand outside the solar system and watch for a human lifetime, you would see no perceptible change in Earth's orbit. But give it 100,000 years, 1,000,000 years, and the accumulated suggestions from Jupiter and Saturn reshape Earth's path in measurable ways. The mathematical description of these gravitational interactions is both elegant and complex. Each planet in the solar system can be thought of as creating a gravitational potential field, an invisible landscape of gravitational hills and valleys extending throughout space. Earth moves through this landscape, its path influenced by the combined gravitational topography created by all the other planets. When Jupiter and Earth are on the same side of the Sun, Earth feels a slightly stronger pull outward. When they're on opposite sides, the effect reverses. These alternating tugs, repeated with each orbital alignment, gradually reshape Earth's orbit. But it's not just the direct gravitational pulls that matter. There are also indirect effects, where one planet's influence on another planet affects that planet's influence on Earth. For example, Jupiter's gravity affects Mars's orbit, which in turn affects Earth's orbit. These indirect effects create chains of influence that can be surprisingly important over long timescales. It's like a cosmic game of billiards, where every ball affects every other ball, and predicting the long-term outcome requires tracking all the interactions simultaneously. The discovery of how Jupiter and Saturn influence Earth's orbit is part of a larger story about humanity's growing understanding of the solar system as a dynamical system. In the 18th century, mathematicians like Pierre-Simon Laplace developed the mathematics of celestial mechanics to a high art, showing how to calculate planetary perturbations using infinite series expansions. Laplace famously claimed that given the current positions and velocities of all particles in the universe, the future could be calculated with perfect precision, a view now known as Laplacian determinism. But in the 20th century, with the advent of chaos theory and powerful computers, we learned that the solar system, while deterministic, is also chaotic over long timescales. Small uncertainties in current conditions grow exponentially, making precise predictions impossible beyond a certain time horizon. This doesn't mean the solar system is random, it still follows Newton's and Einstein's laws precisely, but it does mean that tiny differences, smaller than we can possibly measure, eventually lead to completely different orbital configurations. The role of Jupiter in stabilizing Earth's orbit is particularly fascinating. While Jupiter causes perturbations that change Earth's orbital eccentricity, it also shields the inner solar system from many potential orbital disruptions. Jupiter's massive gravity acts like a goalkeeper, deflecting or capturing many comets and asteroids that might otherwise enter the inner solar system and potentially collide with Earth or perturb its orbit. The famous impact of Comet Shoemaker-Levy 9 on Jupiter in 1994, witnessed by telescopes around the world, was a dramatic reminder of Jupiter's protective role. Computer simulations suggest that without Jupiter, Earth's orbit might be less stable over billion-year timescales. The giant planet's gravity helps maintain the overall architecture of the solar system, preventing the terrestrial planets from drifting into configurations that could lead to orbital instabilities or collisions. It's a delicate balance. Too much Jupiter-like influence could destabilize Earth's orbit, while too little might allow other perturbations to accumulate dangerously. Saturn plays a more subtle but still important role in Earth's orbital evolution. Its gravitational influence on Earth is weaker than Jupiter's due to its greater distance, but Saturn's interactions with Jupiter create combined effects that can be more significant than either planet alone. When Jupiter and Saturn align on the same side of the Sun, their combined gravitational pull creates a stronger perturbation than when they're separated. These alignments occur about every 20 years and have been observed by astronomers for millennia. Ancient Chinese astronomers called them great conjunctions and considered them astronomically significant. The influence of the giant planets on Earth's orbital eccentricity operates through several mechanisms. One is direct gravitational perturbation, where the giant's gravity directly alters Earth's velocity and therefore its orbital shape. Another is through secular resonances, where the rate at which Earth's orbital orientation precesses matches the rate of change of some combination of the giant planet's orbital elements. These resonances can cause Earth's eccentricity to oscillate with specific periods and amplitudes. The most important secular resonance affecting Earth's eccentricity involves a combination of Jupiter's and Saturn's orbital precession rates. This resonance drives one of the major components of Earth's eccentricity variation, contributing to the complex pattern of overlapping cycles that characterizes Earth's orbital evolution. The mathematics describing these resonances involves solving systems of differential equations that account for all the gravitational interactions simultaneously, a task that would be impossible without modern computers. Recent research has revealed even more subtle ways that the giant planets influence Earth's orbit. For instance, the giant planet's gravity slightly deforms the Sun itself, causing it to bulge at the equator. This bulge creates an additional gravitational field that affects the inner planet's orbits. While this effect is tiny, it becomes significant over millions of years and must be included in precise orbital calculations. The study of how Jupiter and Saturn influence Earth's orbit has practical applications beyond understanding our planet's past and future. The same gravitational dynamics that shape Earth's orbit also affect spacecraft trajectories. Mission planners use their understanding of planetary perturbations to design efficient trajectories that take advantage of gravitational assists, using a planet's gravity to change a spacecraft's speed and direction without using fuel. The Voyager missions, which visited all 4 giant planets, were only possible because of a rare alignment that occurs about every 175 years. allowing a single spacecraft to use gravitational assists to visit all the outer planets. As our ability to measure and model planetary orbits improves, we continue to discover new subtleties in how the planets influence each other. For example, recent studies have shown that the asteroid belt between Mars and Jupiter contains several regions where asteroids can remain stable for billions of years, despite being relatively close to Jupiter. These stable zones exist because of complex resonance relationships that create gravitational safe harbors where Jupiter's perturbations cancel out rather than accumulate. The influence of Jupiter and Saturn on Earth's orbit also connects to broader questions about planetary system architecture and habitability. Studies of exoplanetary systems, planets orbiting other stars, have shown that many systems have giant planets in very different configurations from our own. Some have hot Jupiters, giant planets orbiting very close to their stars, which would completely destabilize any Earth-like planets in the habitable zone. Others have giants in highly eccentric orbits that would similarly disrupt terrestrial planets. This makes us appreciate the relatively circular orbits of Jupiter and Saturn in our own solar system. If Jupiter had a highly eccentric orbit, swinging close to the inner solar system at perihelion, Earth's orbit would be much less stable. Life as we know it might never have had the billions of years of relatively stable conditions needed to evolve. The configuration of our giant planets, seemingly arranged by chance during the solar system's formation, turns out to be crucial for Earth's habitability. The gravitational influence of the giants extends beyond just orbital shape. They also affect the distribution of small bodies in the solar system, asteroids, comets, and meteoroids, which can impact Earth and affect its evolution. Jupiter's gravity creates gaps in the asteroid belt called Kirkwood gaps, where orbital resonances with Jupiter make orbits unstable. These gaps affect which asteroids can potentially be perturbed into Earth-crossing orbits. Similarly, Jupiter and Saturn influence the orbits of comets from the outer solar system. Long-period comets from the Oort cloud can have their orbits altered by close encounters with the giant planets, sometimes being ejected from the solar system entirely, sometimes being captured into shorter orbits, and occasionally being directed toward the inner solar system where they might impact Earth. The rate of cometary impacts on Earth over geological time is partly controlled by the orbital configurations of the giant planets. As you contemplate these vast gravitational relationships tonight, consider how they represent a kind of cosmic communication. Jupiter and Saturn speak to Earth not with light or sound, but with gravity, their messages travelling at the speed of light across hundreds of millions of miles of space. Earth receives these messages and responds, adjusting its orbit in tiny increments that accumulate over millennia into significant changes. This gravitational dialogue has been going on since the solar system formed, and it will continue until the Sun exhausts its nuclear fuel billions of years from now. Every moment Earth feels the gentle pull of the giants, a force so weak you could never perceive it directly but so persistent that it reshapes our planet's path through space. It's a reminder that we're not isolated on Earth. We're part of a gravitationally bound family of worlds, all influencing each other in an eternal cosmic dance. The precision with which we can now calculate these influences is a testament to human ingenuity. We've gone from barely being able to predict planetary positions a few years in advance to being able to calculate orbital evolution over millions of years. This capability requires not just powerful computers, but also exquisitely accurate measurements of planetary positions and masses, sophisticated mathematical techniques for solving complex differential equations, and deep physical understanding of gravitational dynamics. In the silence between stars, our moon holds our hand with a grip both tender and firm, a celestial companion that has been with us since Earth's violent youth. This pale guardian, born from cosmic catastrophe, when a Mars-sized body collided with the young Earth over 4 billion years ago, doesn't just light our nights and pull our tides, it plays a subtle but crucial role in the stability of Earth's orbit and rotation. Lunar laser ranging, beams of light touching reflectors left by Apollo astronauts on the lunar surface, shows us a partnership of extraordinary precision, a dance of tides and torque, a gentle exchange of energy that steadies our cosmic journey. The Moon is unique among the satellites of the inner solar system. It's unusually large relative to its planet, about 1/4 Earth's diameter and 1/81 its mass. For comparison, the largest moons of Mars are tiny captured asteroids, mere pebbles compared to our Moon. This size relationship makes the Earth-Moon system almost a double planet, with both bodies orbiting their common centre of mass, which lies about 1,000 miles beneath Earth's surface. This shared dance affects not just Earth's rotation and tides, but also, in subtle ways, the shape and stability of Earth's orbit around the Sun. Scientists have observed that the Moon's pull shapes Earth's spin and wobble in ways both obvious and subtle. The most familiar effect is the ocean tides, those twice-daily rises and falls of sea level that have rhythmed human life in coastal regions since time immemorial. But the Moon's influence extends far beyond the seas. It raises tides in Earth's solid body too. The ground beneath your feet rises and falls by about a foot twice each day, though so gradually you never notice. It creates tides in the atmosphere, subtle variations in air pressure that influence weather patterns. And through all these tidal interactions, the Moon is slowly stealing Earth's rotational energy, causing our days to gradually lengthen while the Moon itself spirals slowly outward. The Moon's role in Earth's orbital eccentricity is subtler, quieter than the giants Jupiter and Saturn, yet it's part of the chamber ensemble that keeps the rhythm of our cosmic dance. While the Moon doesn't significantly change the shape of Earth's orbit around the Sun directly, it does affect how Earth responds to the gravitational perturbations from other planets. The Moon's gravity stabilizes Earth's axial tilt, preventing the wild variations that might otherwise occur, and this stability indirectly affects how orbital eccentricity variations translate into climate changes. Consider this. The Moon's presence tames wildness, smoothing some variations that might otherwise roam unchecked through the Earth system. Without the Moon, Earth's obliquity, the tilt of its axis, could vary chaotically from nearly degrees to 85 degrees or more over millions of years. Such extreme variations would cause dramatic climate changes that would make our current ice age cycles look gentle by comparison. With the Moon's stabilizing influence, Earth's tilt varies only between about 22.1 and 24.5 degrees, a range small enough to allow for relatively stable climate conditions over geological time. And yet, even guardians sway. Perhaps the balance is not a fixed line, but a cradle, rocking softly through time. The Moon itself is not unchanging. It's slowly moving away from Earth at a rate of about 1.5 inches per year, about the same speed your fingernails grow. This recession is caused by tidal friction. As the Moon raises tides on Earth, Earth's rotation carries those tidal bulges slightly ahead of the Moon's position. The gravitational pull of these offset bulges accelerates the Moon in its orbit, causing it to spiral slowly outward, while Earth's rotation gradually slows. This process has been going on since the Moon formed. When it first coalesced from the debris of that ancient collision, the Moon was much closer to Earth, perhaps only 15,000 miles away compared to its current distance of about 239,000 miles. Earth's day was much shorter then too, perhaps only 6 hours long. Over billions of years, tidal friction has transferred angular momentum from Earth's rotation to the Moon's orbit, lengthening our days and pushing the Moon farther away. The evidence for this ongoing process comes from multiple sources. Fossil corals from 400 million years ago show growth patterns indicating that a year then contained about 400 days, meaning each day was only about 22 hours long. Ancient tidal deposits called tidal rhythmites preserve patterns of daily, monthly and yearly cycles from hundreds of millions of years ago, allowing geologists to count the number of days in ancient months and years. All these records tell the same story. Earth's rotation is slowing, days are getting longer, and the Moon is receding. The most precise measurements come from lunar laser ranging experiments that have been ongoing since the Apollo missions. Retroreflectors, special mirrors that reflect light directly back to its source, were placed on the Moon by Apollo 11, 14 and 15 astronauts, and by 2 Soviet robotic landers. By timing laser pulses bounced off these reflectors, scientists can measure the Earth-Moon distance to an accuracy of about 1 millimeter. These measurements have confirmed the Moon's recession and revealed subtle variations in the Moon's orbit caused by its non-spherical shape and non-uniform internal structure. These laser-ranging experiments have revealed other fascinating aspects of the Earth-Moon system. They've shown that the Moon has a small liquid core detected by tiny variations in its rotation. They've measured the gradual decrease in Earth's rotation rate with extraordinary precision. They've tested Einstein's theory of general relativity by looking for tiny deviations in the Moon's orbit that would occur if gravity worked differently than Einstein predicted. So far, general relativity has passed every test. The Moon's influence on Earth's orbital stability operates through several mechanisms. First, the Moon's gravity creates a torque on Earth's equatorial bulge, the slight flattening of Earth caused by its rotation. This torque causes Earth's axis to precess, tracing out a cone in space over about 26,000 years. This precession is relatively regular and predictable, unlike the chaotic variations that might occur without the Moon's stabilizing influence. Second, the Moon's orbital plane is inclined about 5 degrees to Earth's orbital plane around the Sun, and this inclination processes with an 18.6-year period. This creates a complex pattern of gravitational torques that affect Earth's rotation and axial orientation. These lunar-induced variations are small but measurable, and they must be accounted for in precise calculations of Earth's long-term orbital evolution. Third, the Moon affects how Earth responds to perturbations from other planets. The Earth-Moon system has a certain amount of angular momentum that must be conserved. When Jupiter or Saturn perturbs Earth's orbit, the Moon's presence affects how that perturbation is distributed between changes in Earth's orbit and changes in the Moon's orbit around Earth. It's like a flywheel that provides rotational stability, damping out variations that might otherwise grow larger. The Moon's recession has profound implications for Earth's future orbital stability. As the Moon moves farther away, its stabilizing influence on Earth's axial tilt weakens. Models suggest that in about 1.5 billion years, the Moon will be far enough away that it can no longer prevent large variations in Earth's obliquity. At that point, Earth's tilt could begin to vary chaotically, potentially swinging from nearly upright to nearly sideways over millions of years. Such extreme variations in axial tilt would cause dramatic climate changes. With no tilt, there would be no seasons. The equator would always be hot and the poles always frozen. With extreme tilt, one pole would point almost directly at the Sun for part of the year, experiencing continuous daylight and extreme heat, while the other pole would be in continuous darkness and extreme cold. Then, half a year later, the situation would reverse. Such conditions would make it very difficult for complex life to survive. But this destabilization is still far in the future, so far that other factors may intervene first. The Sun is gradually growing brighter as it ages, and, in about 1 billion years, it may be bright enough to trigger a runaway greenhouse effect on Earth, boiling away the oceans regardless of orbital configuration. The timescales of these various processes, lunar recession, solar brightening, orbital destabilization, are all comparable, making Earth's far future uncertain and dependent on the complex interplay of multiple factors. The Moon also influences Earth's orbital eccentricity through its effect on Earth's shape. Earth is not a perfect sphere. It's slightly flattened at the poles due to its rotation, and it has other smaller deviations from sphericity due to the uneven distribution of continents and oceans. The Moon's gravity acts differently on these various parts of Earth, creating torques that can affect Earth's orientation in space. While these effects are small compared to the direct gravitational perturbations from other planets, they contribute to the overall complexity of Earth's orbital evolution. The tidal interaction between Earth and the Moon also dissipates an enormous amount of energy, about 3.5 terawatts, roughly equal to twice humanity's total power consumption. This energy comes ultimately from Earth's rotation and is converted to heat through friction in ocean waters as they slosh back and forth with the tides. This tidal heating has important effects on ocean circulation and mixing, bringing nutrients from the deep ocean to the surface and affecting global climate patterns. Some scientists have suggested that the Moon's tidal effects may have been crucial for the origin and evolution of life on Earth. Tidal pools, areas that are alternately covered and exposed by tides, create unique environments where complex chemistry can occur. The concentration of chemicals in evaporating tidal pools might have helped catalyze the formation of the first self-replicating molecules. The mixing caused by tides helps distribute nutrients and maintain ocean chemistry. And the stability provided by the Moon's presence gave life the relatively constant conditions it needed to evolve from simple cells to complex organisms over billions of years. The Moon's influence extends even to Earth's deep interior. Tidal heating caused by the Moon may help maintain Earth's magnetic field by contributing to convection in the liquid outer core. Earth's magnetic field shields us from harmful solar and cosmic radiation, and without it, Earth's atmosphere might have been stripped away by the solar wind long ago, as appears to have happened to Mars. so the Moon's presence may be essential not just for orbital stability, but for maintaining the conditions that allow Earth to retain its atmosphere and water. As you lie there tonight, perhaps you can see the Moon through your window, that familiar face that has watched over Earth for billions of years. Every culture in human history has gazed up at the Moon, told stories about it, used it to mark time and navigate, but only in the last few decades have we understood the Moon's true importance as Earth's orbital guardian, the celestial companion that keeps our planet stable enough for life to flourish. The Moon tonight is slowly receding, moving away at that fingernail's pace that seems negligible on human timescales, but adds up to miles over millions of years. The Earth beneath you is rotating slightly slower than it did yesterday, though the difference is only about 20 microseconds. These changes are so slow, so patient, that they make even the orbital eccentricity variations we've been discussing seem rapid by comparison. Yet there's something profound in this slow celestial separation. The Moon that the dinosaurs saw was closer and larger in the sky than the Moon we see. The Moon that our distant descendants will see millions of years from now will be smaller, more distant, no longer able to completely cover the Sun during solar eclipses. We live in a special time when the Moon is just the right distance to create perfect solar eclipses, where the Moon's disk exactly covers the Sun's disk, allowing us to see the solar corona in all its glory. Chapter 6. Clocks in Starlight. How we measure the orbit we dream. Scientists have found many clocks for this slow story of Earth's orbital evolution, each one revealing different aspects of our planet's patient dance through space. Gaia, the European Space Agency's star mapping satellite, is creating a three-dimensional map of over 1 billion stars in our galaxy, refining our celestial reference frame with unprecedented precision. JPL's Horizons Ephemerides, maintained by NASA's Jet Propulsion Laboratory, charts planetary paths with such accuracy that we can land spacecraft on Mars and thread probes through the gaps in Saturn's rings. Ancient eclipse records, preserved on clay tablets and silk scrolls, whisper to us from civilizations long vanished, their observations of darkened suns and blood moons allowing us to trace Earth's orbital changes across millennia of human history. Observations suggest that ice cores drilled from Antarctica and Greenland, coral bands growing in tropical seas, and lake sediments accumulating layer by layer all keep time with climate rhythms tied to orbital shifts. Earth archives its own breath in these natural libraries, writing its autobiography in isotopes and minerals, in the shells of microscopic creatures and the growth rings of ancient trees. Each of these records is a clock, marking the passage of orbital time in its own unique way. Consider the possibility that a spacecraft's radio echo, travelling at the speed of light across millions of miles, a telescope's measured angle precise to millionths of a degree, and a fossil's subtle growth ring laid down 400 million years ago all agree on the same cosmic lullaby. They're all measuring the same fundamental phenomenon, Earth's slowly changing orbit, but from radically different perspectives and timescales. And so, measuring becomes a form of listening, long, patient and kind. The story of how we learn to measure Earth's orbital variations is itself a journey through human ingenuity and technological advancement. Ancient astronomers, working with nothing but their eyes and simple instruments, managed to track the positions of planets with remarkable accuracy. The Babylonians recorded eclipses on clay tablets over 2,500 years ago, observations that modern astronomers still use to study long-term changes in Earth's rotation and orbital motion. Chinese astronomers documented guest stars, supernovae, and planetary conjunctions for over 2 millennia, creating an invaluable record of celestial events. But detecting the slow changes in Earth's orbital eccentricity required a leap in both theoretical understanding and observational precision. It wasn't enough to know where planets were. We needed to know where they were to extraordinary accuracy, and we needed to track these positions over long periods of time. This required the development of precise timekeeping, accurate star catalogues, and mathematical techniques for analysing orbital motion. The invention of the telescope in the early 1600s revolutionised astronomy, but even more important for orbital measurements was the development of precision instruments for measuring celestial positions. The transit circle, the meridian telescope, the heliometer. These instruments, developed and refined over centuries, allowed astronomers to measure the positions of stars and planets to ever greater accuracy. By the late 1800s, photographic plates allowed astronomers to record celestial positions permanently, creating an archive that could be remeasured as techniques improved. The 20th century brought radio astronomy and radar, allowing us to measure distances in the solar system directly, rather than inferring them from angles. By bouncing radar signals off Venus and Mars, astronomers could determine the scale of the solar system to unprecedented accuracy. This was crucial for understanding orbital dynamics, because many gravitational effects depend on the exact distances between planets. Space-based observations have transformed our ability to measure Earth's orbit. Satellites above Earth's atmosphere can observe continuously without the distortions caused by air turbulence. They can detect wavelengths of light that don't reach Earth's surface, and they can maintain stable platforms for extraordinarily precise measurements over long periods. The Gaia mission, launched in 2013, represents the current pinnacle of astrometric precision, the measurement of star positions. Gaia is measuring the positions, distances and motions of over 1 billion stars with micro-arc-second precision. That's equivalent to measuring the width of a human hair from 1,000 miles away. This stellar reference frame allows us to determine Earth's position and motion in space with unprecedented accuracy. But Gaia does more than just measure where stars are, it measures how they're moving. By tracking tiny shifts in stellar positions over its mission lifetime, Gaia can determine the three-dimensional velocities of stars throughout our region of the galaxy. This creates a kinematic reference frame against which we can measure Earth's orbital motion with extraordinary precision. The importance of having an accurate reference frame cannot be overstated. To measure how Earth's orbit changes, we need fixed points against which to measure. But in space, nothing is truly fixed. Everything is in motion relative to everything else. The stars that seem fixed in our night sky are actually hurtling through space at hundreds of kilometers per second. Even distant galaxies, which might seem like ultimate reference points, are moving due to the expansion of the universe and gravitational interactions with other galaxies. The solution is to use statistical techniques with large numbers of reference objects. By measuring millions or billions of stars, astronomers can define a reference frame that averages out individual stellar motions. Distant quasars, the bright cores of galaxies billions of light years away, provide the most stable reference points because they're so far away that their apparent motions are negligible, even over centuries. Radio interferometry, particularly very long baseline interferometry, VLBI, provides another way to establish precise reference frames. By combining signals from radio telescopes scattered across Earth or even in space, astronomers can achieve angular resolutions far better than any single telescope could provide. VLBI observations of quasars define the International Celestial Reference Frame, the fundamental coordinate system used for precise astronomical measurements. Closer to home, the Deep Space Network, a collection of large radio antennas in California, Spain and Australia, tracks spacecraft throughout the solar system with extraordinary precision. By measuring the Doppler shift of radio signals from spacecraft, engineers can determine velocities to accuracies of fractions of a millimeter per second. By timing how long signals take to travel to spacecraft and back, they can measure distances to accuracies of meters across billions of kilometers. These spacecraft tracking measurements feed into ephemerides, mathematical models that predict the positions of celestial bodies. JPL's Horizon system is one of the most sophisticated ephemerides ever created, incorporating measurements from ground-based observations, spacecraft tracking, and even gravitational wave detections. It accounts for relativistic effects, asteroid perturbations, and the gradually changing mass of the Sun as it converts hydrogen to helium. The precision of modern ephemerides is staggering. They can predict the position of Mars well enough to land a spacecraft within a few kilometers of a target after a journey of hundreds of millions of kilometers. They can predict when asteroids will occult distant stars to accuracies of seconds and position accuracies of kilometers. They can calculate eclipse paths centuries into the future or past with precision sufficient for historical dating. But for studying Earth's orbital variations over geological time, we need clocks that run for millions of years. This is where geological and paleontological records become invaluable. These natural archives preserve information about past climates, which were influenced by orbital variations, allowing us to work backward to determine what Earth's orbit must have been like in the distant past. Ice cores are among the most valuable of these natural clocks. As snow falls on ice sheets in Antarctica and Greenland, it traps tiny bubbles of atmosphere. Over time, this snow compresses into ice, preserving a record of atmospheric composition going back hundreds of thousands of years. By analysing the isotopic composition of the ice and the trapped gases, scientists can reconstruct past temperatures and greenhouse gas concentrations. The longest ice core record comes from Antarctica and extends back about 800,000 years. In this record, scientists can clearly see the signature of orbital cycles. Temperature variations show periodicities matching the predicted cycles of eccentricity, obliquity, and precession. The correspondence is so clear that ice core chronologies are often fine-tuned using orbital calculations, a technique called orbital tuning. But ice cores only take us back 1 million years or so. For deeper time, we turn to ocean sediments. The deep ocean floor accumulates sediment very slowly, sometimes only millimeters per 1,000 years. But this slow accumulation can continue for millions of years, creating records that extend far into the past. The microscopic shells of foraminifera and other marine organisms preserve information about ocean temperature and ice volume in their isotopic composition. By analysing long sediment cores from the ocean floor, scientists have reconstructed climate variations going back tens of millions of years. These records show clear evidence of orbital cycles throughout this entire period, though the relative importance of different cycles has changed over time. For instance, before about 1 million years ago, the 40,000-year obliquity cycle dominated climate variations. After that, the 100,000-year eccentricity cycle became more prominent, though scientists still debate exactly why this transition occurred. Lake sediments provide another type of orbital clock. In lakes that experience seasonal variations in sedimentation, perhaps lighter sediments in summer and darker in winter, annual layers called varves can form. By counting these layers and analysing their composition, scientists can create detailed records of climate variations. Some lake records extend back millions of years, preserving orbital signals. In the thickness and composition of sediment layers, tree rings offer precise annual resolution but only extend back thousands of years. Still, they're valuable for calibrating other dating methods and for studying recent climate variations. The width and density of tree rings reflect growing conditions, which are influenced by temperature and precipitation. By analysing trees from different regions and times, scientists can reconstruct climate patterns and look for orbital influences on timescales of centuries to millennia. Coral growth bands work similarly to tree rings but in marine environments. Corals add new skeleton material in bands that can be daily, monthly, and annual. Ancient fossil corals preserve these growth patterns, allowing scientists to count the number of days in a year millions of years ago. This provides direct evidence that Earth's rotation has been slowing over geological time due to tidal friction. Speleothems, cave formations like stalactites and stalagmites, provide another climate archive. These formations grow as mineral-rich water drips through caves, and their growth rate and chemical composition reflect climate conditions above the cave. Some speleothems preserve annual growth bands, while others can be dated using radiometric techniques. They've proven particularly valuable for studying climate variations over the past few 100,000 years. Even the magnetic field reversals recorded in rocks provide a kind of clock. Earth's magnetic field occasionally reverses, with north and south poles swapping positions. These reversals are recorded in volcanic rocks and sediments as they cool or settle, creating a pattern of normal and reversed magnetization that can be traced globally. While not directly related to orbital variations, this magnetostratigraphy provides a time framework for dating geological records that preserve orbital signals. The integration of all these different records, astronomical observations, spacecraft tracking, ice cores, ocean sediments, and more, requires sophisticated mathematical and statistical techniques. Each type of record has its own uncertainties, biases, and limitations. Ice cores might have dating uncertainties or be affected by ice flow. Sediment records might have varying accumulation rates or be disturbed by ocean currents. Astronomical calculations become increasingly uncertain going back in time due to chaotic dynamics. Scientists use various methods to cross-check and calibrate these different records. Radiometric dating provides absolute ages for some materials. Volcanic ash layers that can be traced across different records provide time markers. Magnetic reversals recorded in different types of rocks provide global synchronization points. By combining multiple lines of evidence, scientists can create robust chronologies that extend millions of years into the past. The mathematical techniques for extracting orbital signals from geological records have become increasingly sophisticated. Spectral analysis can identify periodic signals in noisy data. Wavelet analysis can track how the strength and frequency of cycles change over time. Bayesian statistical methods can combine different types of data while properly accounting for uncertainties. Machine learning algorithms can identify subtle patterns that might be missed by traditional analysis. One of the most powerful techniques is the comparison of geological records with astronomical calculations. By calculating Earth's orbital parameters going back millions of years and comparing these with climate records, scientists can test whether orbital theory correctly predicts observed climate variations. The match is often remarkably good, providing strong support for the orbital theory of climate change. But there are also discrepancies and mysteries. The 100,000-year problem mentioned earlier, why the relatively weak eccentricity forcing produces the strongest climate signal in recent geological time, remains not fully resolved. There are periods in Earth history when orbital signals seem weak or absent in climate records. There are times when climate changes appear to lead orbital forcing rather than lag it. These puzzles drive continued research and refinement of our understanding. The precision of orbital measurements continues to improve with new technology. Future space missions will map stellar positions even more accurately than Gaia. Gravitational wave detectors may provide new ways to test general relativity and measure the properties of massive bodies. Quantum sensors might achieve sensitivities that seem impossible with current technology. Laser ranging to the Moon will continue with improved retroreflectors that may be placed by future lunar missions. These could include larger arrays that return stronger signals, or active transponders that amplify and retransmit laser pulses. Such improvements could increase measurement precision by orders of magnitude, revealing subtle effects that are currently below our detection threshold. Interplanetary laser ranging, bouncing laser beams off retroreflectors on Mars or other planets, could provide direct measurements of planetary orbits with unprecedented precision. This would allow us to detect tiny perturbations that might reveal the presence of undiscovered objects in the outer solar system, or test theories of gravity in new regimes. The continued accumulation of climate records also improves our understanding of orbital influences. Every year, ice cores get a little longer, sediment records extend a little deeper, and our databases of observations grow larger. Long-term monitoring programs track current climate with ever-increasing precision, providing ground truth for understanding how orbital variations translate into climate change. As you drift towards sleep tonight, consider that you are surrounded by clocks, each keeping time in its own way. Your heartbeat marks seconds, your breath marks moments, your daily cycle of sleep and waking marks days. The Moon's phases mark months, Earth's orbit marks years. The growth rings in the wood of your furniture mark decades of some tree's life. The rocks beneath your home mark millions of years of geological time. All these clocks are connected, nested within each other like Russian dolls. Your biological rhythms evolved in response to Earth's rotation and orbit. That rotation and orbit are shaped by gravitational interactions with the Moon and planets. Those interactions unfold according to physical laws that operate throughout the universe. You're not separate from these cosmic rhythms. You're an expression of them, a temporary arrangement of atoms keeping time with the universe. The measurement of Earth's orbital variations is ultimately about understanding our place in the cosmos. By tracking our planet's slowly changing path through space, we learn not just about celestial mechanics, but about climate, evolution, and the conditions that allow life to exist. We discover that Earth is not a static stage on which life plays out, but a dynamic, evolving system shaped by cosmic forces.